for what I assume was a kind introduction, even though I couldn't understand a single word. So it's a pleasure to be here, and I'd like to tell you about a scientific journey, a scientific odyssey that we have been on for thousands of years as we have been trying to understand the fundamental nature of the universe. And there have been many people who have contributed to this vibrant, exciting, wonderful quest. But I think the name that we all know most well associated with this journey, the name that we associate with greatness in the struggle to understand the universe, is Albert Einstein. And as some of you may know, in 1955, in a hospital in Princeton, New Jersey, Einstein was lying in a bed that would turn out to be his last. And in the final moments, final minutes, the final night of his life, he asked his assistant for the pad of paper on which he had been scribbling equations, in the desperate hope that in that final interval that he had left, he might complete a journey that he had been on for the last 30 years. And that journey was the search for what he called the unified theory. The unified theory. This, he dreamed of, would be a theory that could describe perhaps everything in the physical universe. The big things, the small things, everything in between, from one equation, one idea, one master principle that might encapsulate all of physical reality. He didn't find the unified theory. But in the decades since, we have made what we believe is great progress. And that progress has to do with one approach called string theory. Calculation, imagination. Newton won a very different kind of battle for all of us. Because by the time it was safe for him to return to Cambridge University, he would throw into dazzling relief a fundamental fact, a fundamental law about how the universe works. Because in his time away, he discovered what we call the universal law of gravity. Universal law of gravity. It's a law that we still teach to our students around the world today. A very simple law that we all, I think, are familiar with in one form or another. It says that every object in the universe attracts every other with a force of gravity that depends on precisely two things: how big the objects are, their mass, and how far apart of physics they are in space. A thinker for whom there was no such thing as authority. There was no such thing as received wisdom that couldn't be challenged. There was no such thing as questions that had been settled in an earlier age and were no longer ripe for investigation. Because when Albert Einstein took center stage in the search for the deep laws of the universe, everything was put back on the table. And when he began to think about Newton's description of gravity, Einstein realized something was absolutely off, absolutely missing. He realized that Newton's description might be a good approximation to the truth, but it could not be the full story about how gravity works. And the reason for this comes from the kind of questioning that Einstein was famous for. The kind of questioning, really, that is familiar to 5-year-olds, right? 5-year-olds, they encounter any situation and they ask the seemingly simple questions that most of us shoo away as somehow not being vital or important. But Einstein took those kinds of questions seriously. And in this particular case, the question was, how does gravity work? How is it that the sun, which is 93 million miles away from the Earth, with effectively empty space in between them, how is it that the sun can exert an influence on the Earth? Right? I mean, there's no rope connecting the sun and the Earth. There's no arm that reaches out from the sun and grabs hold of the Earth. So what is the mechanism by which gravity exerts the influence that we witness? Now, to try to figure out the answer to that question, Einstein actually went back to the Principia, the book that has all the results that Newton found during his lifetime about mathematics and physics. And perhaps it is worth saying, because it's unusual, that I was quite pleased to learn from the organizers that everybody here was required to read the Principia ideas. In the general theory of relativity, the new picture of gravity, they are subtle. They are elusive. They are fantastically beautiful. But it's best to approach them first by an analogy that many physicists love to use in this context. And the analogy asks you to forget about the universe for a moment, forget about gravity for a moment. Instead, think about a big, huge rubber sheet that's stretched in front of me, nice and taut. And in your mind's eye, imagine I take a little marble and I set it rolling along the surface of the rubber sheet. In your mind's eye, you can picture what will happen. The marble will just roll in a straight line trajectory. Now let me change that simple scenario just a little bit. Take a heavy object, like a bowling ball or a rock, and I put it in the middle of the rubber sheet. Now the rubber sheet will be curved, warped, deformed. If I take that same marble, instead of rolling along the surface of the rubber sheet, in your mind's eye, you can also picture what will happen. The marble will not go in the same straight line trajectory that it did a moment ago. Now the marble will go in a curved trajectory because it's rolling along this curved surface of the rubber sheet. Einstein says, take that little analogy and apply it to the cosmos. Instead of a rubber sheet, imagine space, the environment that's all around us. And instead of a bowling ball or a rock on the rubber sheet, Einstein says that any astronomical body, like the sun, merely by virtue of its presence in space, warps the space around it. And then another object, like the Earth, when it's moving through this warped or curved environment, goes into curved motion for much the same reason that the marble goes in a curved. One of those attempts will actually pass right through the barrier and emerge on the other side, unscathed. It is a small probability, but not a zero probability, and that is the key idea. Because if I do a version of that very experiment, not with a macroscopic object like myself, but with a microscopic particle like an electron, that I fire into a barrier, much like the barrier on the other side of the hall, where the classical ideas say the electron cannot penetrate that barrier, simply can't be done, the quantum laws say there's a chance that the electron can penetrate the barrier. And when you do the experiment over and over and over again, every so often you find the electron does penetrate the barrier. So however weird, however unfamiliar these laws may be, we need to take them very seriously, because they accurately describe what happens down there in the micro realm. Now, the only feature of quantum mechanics that you need to have in mind to understand why there is a conflict with Einstein's general theory of relativity is Heisenberg's uncertainty principle. Heisenberg's uncertainty principle. And just to get a sense, because I really don't know the composition of the audience, nor do I have any idea of hands when you are asked if you've heard of the principle. Of those who did raise their hands, how many of you pretty much understand what this principle really is all about? A smaller number, but still pretty good. Of any of those who just raised their hand on that question, anybody want to just come up and give a little brief summary of what the principle? A few are still. Who would like to take a photo of the speaker talking about Heisenberg? Oh, I guess that must be you. Okay, great. Good, good. So Heisenberg's uncertainty principle, what is it? Well, there are many ways to think about it. One, by analogy, that perhaps is reasonable is this. I don't know much, unfortunately, about Moscow. I was here about 25 years ago and only got here for a second time a day and a half ago. So I don't know how many Chinese restaurants you have here, but if any of you visited Manhattan's Chinatown, you know that there is a category of restaurant in Manhattan's Chinatown where they have what they call a special order menu, which is you walk into the restaurant and you're presented with a menu that has some dishes in column A, other dishes in column B. And the way they set it up is if you order the first dish in column A, you're not allowed to order the corresponding dish in column B. And that is, in a sense, the uncertainty principle. In the following sense. Knowledge of the microscopic realm is very much like that menu, very much like a list that's divided into two columns. And what the uncertainty principle says is, it says if you have knowledge of one feature of the micro realm, that fundamentally compromises your ability to know a corresponding feature of the micro realm from the second list. And in fact, the uncertainty principle says, the more you know about the first item, the less you know about its partner from the second list. The more you know about its partner, the less you can know about the corresponding element from the first list. Now let me give you a concrete example just to make that more specific. If you apply the uncertainty principle to an electron, here's what it says. It says you cannot know where an electron is and how fast it's moving. You can't know both features at the same time. And in fact, the better you know where the electron is, the less you can know about its speed. The more you know about its speed, the less you know about its position. A fundamental level of uncertainty built into the quantum laws describing the microscopic the discussion here is speculative, hypothetical, not proven, not experimentally tested. So we're entering the domain of frontier thinking, and the danger of frontier thinking is everything that I tell you from this point forward could be completely wrong. Could be utter nonsense. I hope it's not. But that's the nature of research. So just try to keep in mind the two categories of material that we are talking about. Okay, so how do we try to resolve this problem between the laws of the small and the laws of the big? Well, the approach called string theory, let me describe back forth to you first, and up down are the only dimensions in the environment. Then the math of string theory doesn't work. It suffers from inconsistencies, much like what happens if you take 1 and divide by 0 on a calculator. You know, the calculator says E, error. You're not allowed to do that. The math of string theory basically gives that same kind of error message if there are only 3 dimensions of space. Some very creative, insightful physicists continue to study the math of string theory and ask themselves, what if the number of dimensions were not 3? What if there were 4 dimensions of space? Would the math work then? No. 5, no. 6, no. 7, kept on going. Remarkably, when they got to 9 dimensions of space, all of the mathematical inconsistencies went away. The math fell into place.
Какой процент американцев верит в Бога? Верите ли вы и вообще отношение к этому? Спасибо. Цените.
It's about 100%. I haven't done a systematic investigation of that, so I don't have the data, but the data has been collected. And it's a substantial fraction that believe in God. My own view is that we just don't know. That none of the work that we do in fundamental physics really has the capacity to answer a question like that. Because no matter what we find in physics, one could always say, well, okay, you've understood the universe ever more deeply, but how do you know there isn't some fundamental divine being behind it all that has set it up for you to find what you have found? And there's no way to rule that out, I think, from fundamental physics. I see no evidence of the need in any of the work that we do for there to be that divine power. But every time I say that, I feel an urge to look skyward and say, well, I'm not really sure, to hedge my bets, because I just don't really know. So I think the way that I deal with it in day-to-day life is, it doesn't affect my work one way or another. If what we are doing is working out the fundamental laws that have been in place, perhaps for an eternity, governing how our universe came to be and how it will evolve for billions of years into the future, if that's all that we are doing, revealing those fundamental laws, I'm thrilled to be part of that process. If, on the other hand, what we are doing is revealing the divine laws set in place by some divine being, well, heck, I'm thrilled to be part of that journey too. So it doesn't really matter to me one way or another, and I'll just keep going to try to gain a deeper understanding of how the universe works.
Спасибо большое. Спасибо за интересное выступление. Вопрос такой у меня. Что вам в жизни дает страсть, вдохновение, энергию? Дополнительные измерения действительно существуют. Это было 6 лет назад. Случилось или нет? Если нет, то откуда нам ждать подтверждений дальше?
Yeah, so the Large Hadron Collider was a little bit delayed, you may know, because there was a problem with one of the magnets which set the machine back some, but it is now functioning spectacularly well. Data is being collected. So far, there's not been a single surprise from the data at the Large Hadron Collider. Now, the optimist, from the perspective of trying to find evidence for extra dimensions or evidence of other things like supersymmetry or evidence of microscopic black holes, things that would really give us some insight into these cutting-edge theories, the optimistic perspective is we just need to wait a little bit longer as the machine continues to build up in its intensity and the data that we get becomes ever more refined, we will find something of the sort that we hope that we would. But it may be the case that we don't find anything at all at the Large Hadron Collider. And the point that's hard to communicate effectively, but it's important to at least try, is that if we find absolutely nothing unexpected at the Large Hadron Collider, or I should say, nothing beyond what we have found in previous experiments, that would actually be a spectacularly profound and interesting result. It would be one that would send us back to the drawing board on things that we've been thinking about for over 30 years. So we would not view finding nothing as a non-result. It would be a very profound result. The problem from a strategic standpoint is it would mean that we need to build an even more powerful machine to try to reach higher energies. And I would not like to be the person that has to say, go in front of a governing body like the United States Department of Energy or whatever governing body you have here, and have to sit in front of a panel of politicians who determine how money is spent and have them say, so, you're here with a request to build another machine. What's your motivation? Well, my motivation is we found this spectacularly interesting result at the Large Hadron Collider, and they say, what is that result? Well, we found nothing. To us, that would be exciting and spectacularly interesting. It's just hard to communicate that. So the hope is that we will find something that is out of the ordinary at the Large Hadron Collider. If not, we'll keep going, and hopefully the capacity and the will to keep going will be there in the water world as well.
Спасибо за прекрасную лекцию. И мы через несколько минут ждем всех на автограф-сессии в фойе на стенде «Вокруг света», где вы сможете подписать у Брайана Грина книжку и оставить ее на память. Спасибо. Нет, не здесь. Автограф-сессия в фойе.
Пожалуйста, проходите.
Thank you for the lecture.
Just parallel with us.
Welcome to St. Petersburg.
Друзья,